Uh, Good morning to all of you, and welcome to the chemical bonding and molecular structure chapter. Today is the second day of myself
Morning,
transacting
sir.
this lesson. Good morning. Okay. Now, in the previous class, yesterday's class, I had discussed very quickly regarding lattice enthalpy, factors affecting lattice enthalpy, and meaning of lattice enthalpy energy also, and ionization energy with regard to this metals, non-metals, formation of ionic bond. Okay, so today I'll be continuing with this chapter. Okay, today is the second day. It's a morning class. I'll have one more class in the afternoon at 12 o'clock. Now today, basically what I want to discuss is something which is called variable electrovalency. Variable electrovalency. Okay. Now, you have heard this word variable valency in your lower classes. Okay. But here there is something called variable electrovalency. Metallic atoms, metallic atoms, they are capable of losing more than one electrons from their valence shell. That is how they exhibit variable valency. An element shows different combining capacity in different ionic compounds. That is, shows different values of electrovalency. So that is how this phenomenon is called variable electrovalency. And this variable electrovalency term is applicable for metallic atoms. It is applicable for metallic atoms mostly. Now, we have to understand what is the main reason for variable electrovalency. Okay, what are the main reasons in fact? So let us discuss those reasons one by one. Okay, now the first reason over here, it is called unstable configuration of the core, the center of the atom. If it is unstable, and then there is a possibility of the electrons being lost, more than one electron being lost from the center of the core. So here, let me read out in detail. The outermost levels of the elements like iron, cobalt, nickel, copper contain only one or two electrons. Okay, like iron, you see, it has two electrons. It has two electrons. Okay, when these two electrons are lost, the remaining part, which is called the core, after losing the two electrons, this part is called the core or the kernel. It becomes unstable. Hence, more electron from the core can be further lost, giving variable electrovalency to the ions. For example, the variable electrovalency of iron is equal to +2 in ferrous compound and equal to +3 in ferric compound. This is Fe +2. After losing two electrons, it becomes Fe +2. Fe +2. Okay. Now, this this 3s2 3p6 3d6, it is unstable. It is unstable. Now let me explain this by introducing a slide over here. On slide over here, I am trying to explain you variable electrovalency. Variable electrovalency. And in this variable electrovalency, the first reason which I am trying to explain is unstable configuration of the core. Now, let us take the example of iron. Iron, its atomic number, you know, it is 26. If you write down the electronic configuration of iron, it is 1s2, 2s2, 2p6, 3s2, 3p6, and then after that 4s2. Okay, then comes 3d, just add 2 4, 10 12 18 20 20 26 6 over here. Okay, now this is 4s2. Now this is an atom of iron. Okay, Now if this atom of iron loses 2 electrons, if it loses 2 electrons from here, okay, so this atom of iron becomes Fe plus plus, which is called the core, which is called the core. Now let us write down the electronic configuration of the core. So the electronic configuration of Fe plus 2 becomes 1s2, 2s2, 2p6, 3s2, 3p6, and then these two are already gone, so we are left with 3d6. Now this is the electronic configuration of Fe plus 2 ion. And in the d orbital, if you see in the d orbital, the 3d orbital, there are altogether 6 electrons. So 1, 2, 3, 4 and 5. So there are 6 electrons. 1, 2, 3, 4, 5 and 6. Okay, now what is done? To make this Fe plus 2 into Fe plus 3, this presence of 6 electrons in the 3D orbital, in the 3D subshell, makes Fe plus 2 what? Unstable. Makes it unstable. Why is Fe plus 2 unstable? Because it is incompletely filled. This orbital is incompletely filled. Incompletely filled. Incompletely filled. Okay. So to make it more stable, this electron is sent away. -1 electron from the d orbital. From the d orbital, the paired up electron is sent. It is taken away. And then we get Fe plus 3, which has electronic configuration of 1s2, 2s2, 2p6, 3s2, 3p6, and then we have 3d5. Now the d orbital has 5 electrons altogether. 5 electrons. 1, 2, 3, 4 and 5. Now this is stable. This is stable. This 3D subshell having 5 electrons, it's more stable. The reason is it is half filled. It is half filled. I mentioned in the previous classes in the previous chapter that half filled and completely filled orbitals are more stable than incompletely filled orbitals. So that is the reason, that is the first reason for an element, metallic element, to exhibit variable electrovalency. So here we can see the two valencies are Fe plus 2 and the other one is Fe plus 3. Okay, so this is the explanation for by taking the example of iron atom. Now let us come back to the previous slide. Now an increase in the nuclear charge, Fe plus 2 is becoming Fe plus 3, tends to prevent the removal of electrons from a lower energy level. For example, cobalt, atomic number 27. Atoms from CO plus 3 ions with great difficulty because third electron are more firmly retained by the cobalt nucleus with positive charge equal to plus 27, which is 1 unit higher than an iron nucleus. Okay, so if you look at cobalt now, let me explain by taking the example of cobalt also. CO plus 3 is cobalt. Why it is more stable? Let me explain it to you. I am trying to explain you variable electrovalency. Variable electrovalency. So cobalt, we know its atomic number is 27. Okay, its electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, then 4s2, then 3d7. The d orbital has, the d subshell has 7 electrons present in its orbital. Now this can lose a total of, if you look at the 4s subshell, there are 2 electrons, and the 3d orbital subshell has 7 electrons. Let us fill them. This is 3d, this one is 4s. So 1, 2, 3, 4 and 5. So 1, 2, 3, 4, 5, 6 and 7. So what happens? This is incompletely filled, this is completely filled. Okay, now here if I make the ion, cobalt ion, CO, look at this, CO plus plus, after losing 2 electrons. After losing 2 electrons, if I remove the 2 electrons, say one from here, okay, it is possible to get CO plus 2. And one more electron from the s orbital can be given away to make it CO plus 3. That is possible. Okay, now have a look over here. The variable electrovalency of copper. Okay, now before that, after losing, after losing, you know, 2 electrons, after losing 2 electrons from the 4s subshell, the electronic configuration of cobalt becomes 1s2, 2s2, 2p6, 3s2, 3p6, 3d7. And after that, again losing one more electron, the electronic configuration becomes similar to that of iron. Again, it becomes stable over here. It becomes stable. Okay, so that is the reason for variable valency. Everybody, every atom, every substance tries to attain stability in one way or the other. So here also, metallic atoms, they are trying to attain stability by losing electrons from their valence shell or the valence orbitals. Okay. Similarly, if you look at the variable electrovalency of copper, it has 2, plus 1 and plus 2. Is easily understood from the electronic configuration given below. Copper atomic number 29 in the ground state. Okay, to make it completely filled and half filled. Copper ion Cu plus 1. The s electron is lost, so it is becoming stable over here. Again, one more electron is lost from the d orbital to make it d9 electrons incompletely filled. So this copper ion Cu plus 2 becomes more reactive. So here we can see Cu plus is more stable than Cu plus plus, which means, in other words, Cu plus 2 is more reactive. Cu plus 2 is more reactive in its compounds. Okay, so this is the first reason to explain you all the reason for variable electrovalency. Now coming to the next reason over here, inert electron pair effect. Inert electron pair effect. Now this inert electron pair effect means the reluctance of the electrons present in the inner orbitals to go away or to leave the kernel. Now some of the heavier elements of p block of the long form of the periodic table, like those of group 3a, gallium, indium, thallium, 4a, germanium, tin, lead, 5a, arsenic, antimony, bismuth, and 6a, tellurium, polonium, show two oxidation states as given below. You can see. Okay, group 4 is tin and lead. Group 5 is antimony, arsenic, antimony, bismuth. Group 6 is tellurium, polonium. Okay, now here tin and lead. Let us understand this by taking the example of tin and lead, because inert electron pair effect is also one of the reasons for elements to show variable electrovalency. Now let me explain this by taking an example over here, by introducing one more slide over here. Now tell me, what is the atomic number of tin? Atomic number of tin, just now you saw atomic number of tin. Try to look back in your textbooks and see what is the atomic number of tin. I have done this in the previous chapter. Try to get the atomic number of tin quickly. Carbon, silicon, germanium, tin and lead. Atomic number of tin is how much? Yes? Atomic number of tin. It is how much? 50. It is 50. What is the atomic number of lead? Atomic number of lead. It is 82. Now, if I write down the electronic configuration of these two elements, tin and lead, I will get a clearer picture. I will get a clearer picture in order to understand properly the what you call this inert pair effect. Okay, so now using the Aufbau principle, using the above principle, I'm going to write down the electronic configuration of first tin. Okay, so here we start with the electronic configuration of tin first. So how do you start? You start with 1s2, 2s2, 2p6, 3s2, yes, 3p6, 4s2. Are you getting it? Electronic configuration of what? I'm talking about the electronic configuration of which element first?
Tin.
Yes, so tell me now. 1s2, 2s2,
2s2,
2p6,
2p6,
3s2,
3s2,
3p6.
3p6,
Then comes after that 3p6 comes
3d10,
3d
3d10, 10,
3d10. After that comes
4s,
4s2. After that
4p.
4p. 4p. 4p how much? 4p6. Now just check the total. Has it come to 50? Just take the total. Has it come to 50? Add. Huh? Has it come 50? Check, check.
No, sir.
No, sir.
How much it is?
36.
It is 36. So we have to increase some more, no?
36.
We have to increase some more orbitals. Do we have to increase some more orbitals? Yes or no?
Yes, sir.
Nobody is speaking. See?
Yes, sir.
Nobody is
Yes,
speaking.
sir.
So what will be the
Yes,
electronic
sir.
configuration now? What will be the electronic configuration now? 4s2, 4p6. After that, what will happen?
4d,
Huh?
4d,
4d how much?
10,
After that,
5s2,
5s2. Then after 5s2,
4p2,
4,
4p2, 5p2,
5p2.
5p.
Okay, 5p2. Okay, good. Now check the total. 2 plus 2, 4, 10, 12, 18, 28, 30, 36, 46, 47, 41, 50. Correct. It is 50. Now, if we remove 2 electrons from here, does tin become Sn plus 2 after the loss of these 2 electrons from the p orbital? Does it
Yes, sir.
become? Okay. Now after the loss of these 2 electrons, this is a subshell, no? Is a shell. 5s, 5p, same principal quantum number. So it is still what you call unstable. What you call? It is unstable. Now here what happens is these 2 electrons present in the 5s subshell, they are reluctant. They are what? Reluctant. Reluctant to lose, to leave. They are reluctant to lose. They don't want to go away. And this effect, it is called inert pair effect. This effect is called what? Inert pair effect.
Inert.
It is called inert pair effect. This effect of the inner electrons to lose, go away, it is called inert pair effect. Are you getting it? Are you getting it?
Yes, sir.
So we have 4d10, 5s2, 5p2. After that, which element I was talking about? But if you remove these 2 electrons also, doesn't tin show Sn plus 2, Sn plus 4, sorry? Isn't this variable valency?
Yes, sir.
It is possible. Now between
Yes.
this valency and this valency, which one is more stable? Which one is more stable? Sn plus 2 is more stable because immediately after the loss of these 2 electrons, the nucleus becomes stronger with plus 50 positive charges, and now it can easily pull 48 electrons more strongly and firmly towards itself. That's why the loss of these 2 electrons become much more difficult. It becomes much more what? Difficult. So that's why Sn plus 2 is more stable. This is because of an effect which is called inert pair effect. It is called inert pair effect. Now, similarly, let us
Sir,
understand. Yes, please ask.
so if it would have lost 4 electrons, the nucleus should pull it more strongly, no?
More strongly, more strongly. But it is not happening like that, no, because this is S subshell. This is P subshell, no? As soon as you remove two
Yes, sir.
electrons, no, what happens? There are only 48 electrons left, no? Now these 48 electrons can
Yes,
be
sir.
pulled more strongly by the nucleus. That's why these two electrons are not willing to go away. And this reluctance of the inner electrons in the inner subshells, it is called inert pair effect. It is called inert pair effect, and this is also one of the reason to what you call explain what you call this variable electrovalency. Okay, now if you look at lead, atomic number is it is 82. So I straight away start with xenon, Xe xenon. Then I can write on 4F14, then 5D10, then 6S2, then 6P2. Okay. Now here after the loss of these two electrons, the nucleus becomes stronger, plus 82. So it will pull these two electrons more strongly. So that is why these two electrons are not willing to go away. And this not willingness, it is called inert pair effect. And this is one of the reasons for elements, metallic elements, to exhibit variable valency. Am I clear? Am I clear to all of you?
Yes, sir.
Okay, so inert pair effect and unstable nature of the core is explained to all of you. Okay, now look at the next paragraph over here. All of these are showing two oxidation states. All of them, see, tellurium plus 4 plus 6, polonium plus 2 plus 4. And in all these examples, the lower oxidation states are more stable because of inert pair effect. Now, these two oxidation states differ from each other by 2 units. The higher oxidation state for most of the element is equal to the group number G, while the lower one are equal to G minus 2 as shown above. The group number oxidation state is obtained when all the Ns and Np electrons from Ns2 and Npx configuration of the p block elements are lost, while the lower oxidation state is obtained when only Np electrons are lost and the Ns electron pair, due to extra stability, remains inert, that is, it is not lost. Such a pair of Ns electrons is called inert electron pair, and the effect caused by this pair is called the inert electron pair effect. That means after losing two electrons from the Np subshell, the Ns electrons, they are reluctant. They are not willing to lose. They are not willing to lose. That is how the ion which is formed acquires extra stability. It acquires an extra stability. So that is how it is exhibiting or showing inert pair effect. Okay, so these are the two important reasons. These are the two important reasons for elements to show variable electrovalency. Now, moving to one more slide over here, variable electrovalency. Okay, this is something which I have already explained you. Now let us go to the next slide in this chapter, properties of ionic compounds. Now, with regard to properties of ionic compounds, we already know that they have high melting points and high boiling points, and they are very strong and require a lot of energy to break. They require a lot of energy to break. That means they possess very high dissociation energy. Their dissociation energy is very, very high. It is very, very high. Okay. Now, the electrostatic forces of attraction between oppositely charged ions lead to the formation of ions. Okay. The electrostatic force between the opposite charged ions, cations and anions, is strong. And if you break them, if you overcome that, then result in the formation of ions. Okay. Now, ionic compounds, they form crystals. These compounds are brittle and break into small pieces easily. That is the reason for the brittleness. The ionic solids are, they are hard. They are hard. The hardness is due to what? Strong electrostatic forces existing between the ions. An ionic solid consists of layers of positive and negative ions. So on top of each other, there are layers, positive, negative, which makes them possess a very strong electrostatic force. Okay, so whenever a force is applied on it, the layer may shift here and there, and the ions having similar charges may come in front of each other, thus thereby repelling each other, and that is how we can break them easily. Okay, then electrovalent compounds. Electrovalent compounds usually dissolve in water and are insoluble in solvents like oil, petrol, kerosene, etc. Ionic compounds do not conduct electricity in the solid state, but they conduct electricity in the molten state only. In comparison to molecular compounds, ionic compounds have higher enthalpies of fusion and vaporization. That means in order to melt them, in order to vaporize them, we need lot of temperature. We have to provide lot of heat energy. Now, besides these properties of ionic compounds, I want to discuss one more property, important property, which is required by you all. And this property, it is called property of ionic compound. This property is important and it is called solubility in water. Solubility, I talked about this that time. Solubility in water. Why are ionic compounds soluble in water? This solubility in water is very, very important. To understand the solubility of an ionic solid in water, again it depends upon two factors. There are two factors. The first factor is called lattice energy. It is called lattice energy. Symbol is delta H lattice. Okay. And the other factor, it is called hydration energy. It is called hydration energy. It is called hydration energy. The symbol for hydration energy is again delta H hydration. Delta H hydration. Now, what are these? I'll explain you first. Okay. Now, this lattice energy is the enthalpy change involved in the formation of 1 mole of an ionic crystal from its constituent gaseous positive and negative ions. So the amount of energy which is involved in the formation of 1 mole of an ionic crystal from where? From its gaseous ions which are oppositely charged, and that is called lattice energy or lattice enthalpy. Whereas hydration energy means the energy, the enthalpy change involved in the hydration. Hydration means combining with water. Hydration of 1 mole of gaseous ions of each type of the ionic solid to dissolve in it, it is called hydration energy. So if 1 mole of the gaseous ions of the solid which get dissolved, which get hydrated in water, and that is called hydration energy. Now here you remember one formula. You remember one formula over here. If if delta H hydration, if delta H hydration, it is greater than delta H lattice, then the salt, ionic salt, then the salt would dissolve in water. Remember this. So there will be direct questions from here. This is the first condition. If delta H hydration, that means the hydration energy is greater than the lattice energy, then the salt would dissolve in the solid. The next is if delta H hydration, it is less than delta H lattice energy, the salt would not dissolve in water, So these are the two things you must remember. Okay. So with regard to solubility of ionic compounds in water. Okay. However, in the second case, you remember the salt will dissolve only if this hydration energy is less than the Gibbs free energy, which I'll discuss about the Gibbs free energy in the chapter chemical thermodynamics. Okay, but
Sir,
yes,
sir, what if both the energies are equal?
if both energies are equal, then it is 50-50. You know, sparingly soluble. Have you heard about sparingly soluble salts?
Yes, sir.
Okay, so that will be the situation. Okay, but here we are not talking about sparingly soluble salts or equating lattice energy with hydration energy. We are talking about if one is bigger than the other, then only the salt will dissolve, and not dissolve. Only these two conditions to be remembered over here for the questions. Am I clear now? Am I clear?
Yes, sir.
Okay, so try to remember these two conditions. You know the meaning of hydration energy, no? The energy which is involved in dissolving 1 mole of the solid crystal salt, okay, to form ions, oppositely charged ions in water. Okay, that is called hydration energy. Whereas lattice energy or lattice enthalpy, it is the energy which is involved in the formation of 1 mole of an ionic crystal from its gaseous ion. This is for formation, this is for dissolution. Okay, so please remember this, very, very important. This is important for your competitive examinations as well. Important for your competitive examinations as well. Okay, now, now there are some more properties of ionic compounds, like there is one property which is called, which can be talked about, which is called stereoisomerism. Stereoisomerism. Stereoisomerism by ionic compounds. Here, the ionic compounds are neither rigid nor directional. That means isomerism which is exhibited in space. When I explained you the chapter organic chemistry, there I was talking about isomerism. Okay, so in three-dimensional space, if compounds have different structural formula in three-dimensional space, but the molecular formula is same, okay, then they exhibit stereoisomerism. But here ionic compounds, they are neither, they are what? They are they are neither they are neither rigid, they are neither rigid nor nor directional. Okay, therefore, therefore they are therefore they are unable to exhibit stereoisomerism. Stereoisomerism. So remember this sentence strongly. Okay. Ionic compounds, they are neither rigid nor directional. Therefore, they are unable to exhibit stereoisomerism. That means they don't have a double bond between the two combining atoms, which means they can be rotated. Okay, they can be rotated here and there. Okay, that is why they will not exhibit stereoisomerism. The other property which can be discussed under the properties of ionic compounds is ionic reactions. Ionic reactions. Now, these are ionic compounds which undergo ionic reactions. Now, this ionic reaction is because of the mutual interaction of the ions. So, that's why the reactions, the reactions, the reactions are fast. The reactions are fast. Ionic compounds undergo very fast reactions because of the presence of what you call ions in them, because of the presence of ions in them in the solution state or in the gaseous state, possible. Okay, so these were the properties which you must go through, okay, which I have discussed later on, like solubility in water with regard to lattice energy and hydration energy. Okay, remember these 2 points properly. And then stereoisomerism and ionic reaction, from where questions are asked generally. Okay, so I hope you got what is the meaning of hydration energy. What is the meaning of hydration energy? Tell me, what is hydration
So
energy?
could you write the definition?
Okay, I'll write it down. Hydration energy. Hydration energy represented as delta H hydration. Delta H hydration. Okay. It is the enthalpy. Enthalpy change. It is the enthalpy change involved in the hydration. In the hydration means formation of ions because of water. In the hydration of 1 mole, 1 mole of gaseous ions, hydration of 1 mole of gaseous ions of of each type, each type of an ionic solid. Ionic solid. Okay, this is the definition for hydration energy. Now, for an ionic compound to be soluble, you know the condition. For an ionic compound to be soluble, what is the condition? Delta H hydration. Delta H hydration must be what? Less than or greater than?
Greater than.
Greater than
Greater than.
delta H lattice. Correct, no? Correct, no? This is one.
Yes, sir.
For an ionic compound, if it is not an ionic compound, then it will be what? Insoluble, no? It will be what? Insoluble. So if it is insoluble means the delta H hydration will be less than delta H lattice. Are you getting it? So we can compare from here. So this, I think this slide becomes a very much summarized slide with respect to the periodic property, what you call the properties of ionic compound, which is called solubility in water. For a compound, ionic compound to be soluble in water, the hydration energy must be greater than the lattice enthalpy. If you remember this, other one is just the opposite over here. Am I clear, my dear boys? Am I clear?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
So it is already time up. So I like to just stop my class over here to meet again in the afternoon at 12 o'clock. Okay, but please hang on over there. Let me record the attendance. Then only you may leave the class. Okay. In the
Yes, sir.
afternoon class, I'll continue with one more property over here for the formation of ionic compounds with respect to the lattice enthalpy. There's a numerical to be done. Okay. So let us come back to the attendance sheet. I am downloading the attendance. Okay, it is downloaded. Now I am leaving the class. Thank you so much. Have a nice day.
Thank you,